So I'm going to start with what I call a pivotal transition in human effort to understand what's going on in nature, okay? And I call that the pivotal transition in scientific thought. And the nature of this transition is the shift from gathering knowledge, gaining knowledge about what's around you, to gaining understanding of what's around you, okay? That's the key part of this shift that I'm going to talk about. So the efforts to gain knowledge about our world and about the skies above was an integral part of every culture, okay? Hindu, Muslim, Jewish, Egyptian, African, everywhere, okay? Native American, all cultures were involved in trying to gather knowledge about nature, about the skies, etc. However, and I will show you plenty of examples of efforts to gather knowledge from many cultures, okay? But what I want to focus on now at this beginning point is that there is one particular difference that took place in one culture, okay? And that difference is what I call gaining understanding, all right? Now, this is an opinion, okay? This is an opinion which I share with many science historians, okay? That this pivotal event took place within one culture, okay? And as an opinion, of course, it's open to debate, all right? So if you feel that I think I'm being too, I'm favoring Greek culture too much, if you think that, and if you think that I should be looking at other cultures like Chinese or Indian or African cultures, I encourage you to look at that and ask yourself, did a similar transformation take place in some other culture that I'm going to try to go through? Did a similar transformation take place? And if you feel strongly that such a transition did take place and you want to express your opinion contradictory to mine and so on, you're welcome to do that, okay? You're welcome to write me a 5-page paper justifying with as much justification as I'm going to try to provide you as to why I felt that this transition from gaining knowledge to gaining understanding took place within one and only one culture, okay? So it's a bold statement, but it is an opinion and it is open to debate, and you're welcome to take me on, all right? Okay. So what I'll try to do is I'll try to show you my reasoning for attributing the special transition to the Greek culture. Okay. Of course, Greece, you all know where Greece is. This is a map of some of the islands. The Greek islands. This is Ithaca. You know, our town was named after one of the Greek islands. In fact, a lot of places around here are named after Greek islands. Syracuse, and also Greek characters. Homer, what else? Okay, if you're going to speak, you have to speak louder because I can't hear you. But there are many areas around here that are named after Greek. And the reason for that is that when it came time to name the places in this area, the person who did that was a Greek scholar. Okay, so he chose a lot of the names from the Greek culture. My favorite place in Greece is this place called Delphi. And has anybody been to Delphi here? Okay. It's a wonderful place to go. It's very serene, very quiet. And the reason I like it is because it's got this most famous temple called the Oracle at Delphi. And the Oracle is a place where predictions are made, right? And so the priestess over here would make predictions about the outcome of wars or the birth and death of kings and so on. And the reason I find this particularly appealing is because it's oracular for the progress of science. Okay, so I feel here is where this transition takes place, and it's sort of like an oracle. This transformation to understanding took place over here. So now let me put this in the context that it deserves. So the Greeks didn't all of a sudden wake up one morning and get all this great wisdom, okay? They, in fact, acquired centuries of knowledge gathered by other cultures, okay? And on the basis of that, they then made the transition. And I'll come back to some of the key events that led to the transition. And I'll give examples from mathematics and astronomy that came from previous cultures, okay? But in fact, there was an awakening, and you can almost say that there's an awakening in all cultures, like in China, Confucius, or in India, Buddha, and so on. There's a sort of an awakening or a movement taking place in different cultures. And I like to equate this event, this moment in history around 650 BC, to an awakening of the Greek culture, where what you're familiar with as Greek philosophy, or Greek philosophers, began to look for rational explanations for natural events. Okay? Now this was a very, very big step forward, radical step forward, because most other explanations for natural events were based on supernatural phenomena, supernatural entities, okay, like gods and so on. And these, in fact, even in the Greek culture, gods are extremely popular. Okay, they explain everything. Okay, but these Greek philosophers took this different turn to provide rational explanations for natural events and dismiss mythical explanations which led to colorful myths about invisible gods and faraway places and so on, even though it was really part of their culture also. Okay, so in all cultures, including the Greek cultures, gods were responsible for earthly phenomenon and celestial activity. Gods always provided the common explanation for most cultures, and I'll give you an example. So the question that will absorb us through the whole semester, okay? If everything falls down, why don't the heavens fall down, okay? What keeps the sun, the moon, the stars in the sky, okay? We all know it's gravity, right? But that whole idea came very slowly, okay, very thinking, okay. But before these ideas came, you know, the Greeks explained the reason that the heavens do not fall down is because the god Atlas supports the heavens. Okay, so there it was, the supernatural explanation. The sun, the moon, the stars don't fall down because Atlas is holding them up. And in many other cultures, it's similar. Okay, in Indian culture, it's the elephant that supports the earth. Well, then what supports the elephant? Well, the turtle supports the elephant. And what supports the turtle? Well, the snake supports the turtle. And so on, okay? So a lot of cultures have similar supernatural explanations. So the difference here is that we're looking at natural laws and at the approach of these few exceptional Greek thinkers who rejected these supernatural explanations and came to the thinking that nature is not subject to the powers and whims of gods and goddesses, and as a result, they needed to try to come up with a natural explanation, what we call natural laws. Okay? And that step is what I call launching the scientific inquiry. That's part of this pivotal transition, okay, from gaining knowledge and trying to explain things away by trying to find this explanation in our reasoning, in nature itself. Okay? Looking for rational explanations derived from reasoning. Okay? Now this development that took place when these Greek philosophers came on the scene was actually part of a very broad cultural and intellectual development that was taking place in Greek culture at the time. So that this scientific turn was just one aspect of a broad intellectual development that was taking place in the Greek culture. Okay? And here I can give you examples of other manifestations of this broad intellectual development which you see in politics, literature, philosophic dialogue, art, and poetry of the Greek culture at the time. Okay? So if we take politics, you see, our word politics actually comes from the Greek word, where polis in Greek means city-state, and kratos means rule. Okay? So, so for example, if you use the idea democracy comes from demos and kratos, where demos means people and kratos means rule. So democracy is the rule of the people, okay, which is what we've inherited now from that Greek culture. Okay, but democracy was not the only model that the Greeks followed, or that the other cultures around that time followed. There was also aristocracy, which meant the rule of the best. Okay, and there was several periods in Greek history when aristocracy ruled the day. Okay. So there's examples from politics to show you that there was transformations taking place in Greek culture at the time. In Greek literature, there was enormous, prolific output from authors like Homer, who wrote the Iliad and the Odyssey, okay, Aristophanes, who wrote plays. How many people have read? Just raise your hand if you've read all these things before. Yeah, so you have a lot of literature majors and Greek scholars over here. Okay, so you can find the connections between what I'm talking about and these aspects of Greek culture that took place at the same time. Okay, so I want to emphasize that there was, in the Greek literature, there was a certain attitude of the authors, like Homer, where in his epic of the Iliad and the Odyssey, he provided the language, okay, the Greek language and the poetry, okay, but he also provided an attitude that was, I think, necessary for the birth of this idea of trying to come up with their own explanations of what's going on, okay? And that attitude is that people can eventually be masters of their own fate, of their own destiny, despite the fact that they have to struggle a lot against a lot of forces, including gods and wars and so on with each other. Some of that is still going on. But just to give you one hopefully convincing example, they really revered this goddess, Athena. Okay? And what I was really struck by was she was a goddess of reason, goddess of wisdom. Okay? Not reason, goddess of wisdom. Okay? So that she was one of the highest goddesses. Okay? So if you go to Athens, there's that famous Parthenon temple, and you are told that at the center of the temple was the statue of the goddess Athena standing there with the scepter. It's true, they're talking about God, okay, they're talking goddesses, but the point is that the goddess has a complete human form, okay? So really they're talking about us, okay? So the point is that the Greek attitude is expressed by how they are choosing the characters of the gods and the goddesses. So in fact, they fashioned many of their gods after us, after our own characters. So the Greek gods made love, they fought wars, they got drunk. So there you have Aphrodite, the goddess of love, okay? And she inspires all kinds of erotic poetry and so on, okay? And there's the Greek god Mars, who's the god of war, and there's Dionysus, who's the god of wine, who was punished by the other gods for releasing the secret of how to make wine from the grapes to the humans, okay? But nevertheless, the point is that they fashioned these gods after the characters of men and women. And they formed an attitude at which you can see in the way the sculptures carved the statues of the gods. So here is the top dog, okay, Zeus, okay? And he is crafted in such a way, in a very noble fashion, in a very towering fashion, okay? And its dignity and poise that express his form, and Homer's idea that yes, we are in charge or in control of our destiny, even though we may have to fight against a lot of different kind of battles. And this attitude, again, you can see, by the way, in a very interesting place on our own campus, that the gods who stood for reason, like for example Apollo, okay, always towered over or dominated the gods who characterize passion and emotion. So for example, here Apollo, who's considered to be the god of lots of things, medicine and healing and light and truth and archery and all, he's kind of suppressing the god Centaur, who is half beast and half man, ruled by emotion. Half beast, right? So have anybody seen this replica on campus? Nobody? Okay, I think it's in Goldwyn Smith in the admissions. You go by that corridor, it's in there. So go look for it, okay? There's a lot of... So dialogue and debate were in fact very important parts of Greek culture, as you can see from their paintings and from their other works of art. So here you can see people collected at the agora. The agora stands for the market, okay? And in the market they argue about lots of things, including the price. And here, this is a vase where they show that here's the god Zeus sitting on his throne, and he's arguing with this other god. I don't know what his name is, but the point is that both in the assembly of gods and in the assembly of humans, debate was considered to be a very natural thing. And in fact, the Greeks are always talking and debating with each other. I wonder if there's some people from Greek culture heritage over here. If you disagree with me, feel free to complain or email. But I think the Greek culture tends to argue a lot. Okay, so philosophic dialogue and debate were critical components of this culture, and it was very important for the development of science. Okay, so in this agora, what kind of topics were they probably debating besides the trivial topics of everyday life? Okay, and the topics that we are interested in, that they're debating, is what is the shape of the Earth? Okay, is it round or is it flat? Is there an end to the Earth if it's flat? Okay, do you fall off? Something that occupied our Western culture for a long time. And if this Earth, what supports the Earth? What supports the heavens? Things that I already talked about. Okay, so now I want to discuss some of the reasons why it was the Greek culture that was ripe for taking this different approach. Okay, so I'm going to give you two main reasons. I'm sure that historians have many more. I like these two reasons because they're most relevant to how the knowledge, how the transformation took place. One was, as I said before, that while the Greeks were expanding their frontiers, while they moved from the islands to France and to Egypt and Babylon and so on, they absorbed the knowledge of all these cultures. Okay, so they learned a lot of stuff. And in fact, here you can see the Greek islands over here. Here's Athens, and you see Babylon is not too far away, so they could easily sail out there. And Egypt is over here. And so they did, in fact, expand their culture in many directions, and they learned from these different cultures a lot of their knowledge. Okay. So that was one reason. And the second reason is that they had a unique reaction to their expanding frontier. It was not only towards the east, but towards the west. They had a unique reaction because they were a maritime culture, okay, who had to figure out things for themselves, and they had to survive in this unfamiliar territory of these new lands. And when they came to these new lands, they needed to have a new approach to thrive in this new unfamiliar territory. It's sort of a little bit like the Western expansion in the United States. Okay. So now let's go look a little bit closer at the influence of some of these cultures that existed for a long time before the Greeks. Okay. So Egypt was the civilization that grew up around the edges of the river Nile. Okay. And it was called the life-giving river, okay? And it was, in fact, an extremely productive culture. And the Greeks learned, and they saw a lot of wonderful things from this culture, including engineering, technology, mathematics. And you can see the accomplishments of the Greek culture from some of the monuments that they've left behind, the pyramids and the Sphinx and so on. How many people have visited Egypt? Okay, good. We don't have that many world travelers in this class. Okay, there's one over there. Okay, and these are immense monuments. We still don't quite know how they made these, or how they put together such gigantic structures. But nevertheless, the Greeks saw it, and they learned about how advanced these cultures were. Babylon, which is at the confluence of these two rivers, Tigris and Euphrates. Egypt is at the river Nile. Babylon is now Iraq. Okay, so this civilization was the land of this temple ziggurat and Hammurabi, who was the first person who wrote down the laws of civilization on these pillars, and then also he had commissioned this wonderful garden, the Hanging Gardens, of which this is a more recent painting. And there was also the effort to build this Tower of Babel, where the different civilizations got together to build this enormous structure, sort of like the skyscrapers that we build today. And so Egypt and Babylon were tremendously advanced cultures, okay? And they developed these cultures were there hundreds and thousands of years before the Greeks came on the scene, and they were far more developed, okay? For example, they wrote things down. They already had the technique of writing everything down. And here's a picture of an Egyptian scribe, and here is a Babylonian tablet. Anybody knows where you can go see a Babylonian tablet? Anybody seen a Babylonian tablet? It's in the Louvre Museum. Okay, if you go to Paris and you go there, you can see lots of Babylonian tablets there. And the point here, of course, is that while the Greek poets like Homer was writing beautiful poetry, coming up with beautiful poetry, But that poetry was passed on from generation to generation by word of mouth. Okay? They had no way of writing it down. Okay? And eventually it was written down much later. Okay? But in the meantime, Egypt and Babylon were already writing down the accomplishments of their culture. Okay? They had the technology of preserving dead bodies so advanced that some of these mummies are still in a great state of preservation today. Okay? So they obviously knew a lot of chemistry and a lot about the human anatomy of how to avoid it from completely decomposing. Okay? So I'm sure how many people have seen the Tutankhamun exhibit, Chicago, New York, etc. Right? And so it's quite impressive that the technology that they had for working metals, etc., was again in that period extremely advanced. So coming now closer to scientific developments related to science, let me talk about the mathematics that the Egyptians had. The Egyptians developed a lot of mathematics from the problem of surveying. And they needed to survey quite often because, as I said, this civilization grew up around the banks of the River Nile. And the River Nile would flood every year, okay, and all the property boundaries would get washed out. And so they would bring in the official surveyors every season and mark out the land. Okay? So this need to resurvey the land led to the rules of how to make a right angle triangle, right angle rectangle, okay, or how to measure the areas of rectangles and measure the area of triangles and so on. So they had developed simple procedures to define a right angle. And the right angle was defined by taking a rope and putting a marker here. So they say the rope was 12 units long. Then you would take a marker and put it at 3 units, another marker at 4 units, and another marker that left 5 units behind. And you'd fold it up into a triangle. And such a triangle they knew would define the right angle. And now that way they could define the right angle and draw the rectangle. Okay? So this technology of the right angle triangle they knew. Okay? And they knew how to figure out the area of a rectangle, which is the base times the height, or the area of a triangle, which is 1/2 the base times the height, which actually is a nice homework problem for you guys to figure out as to why the area of a triangle is half the area of a rectangle. But I'll leave that to you. So while they did these enormous constructions and these monuments, these tools and the knowledge that they needed, okay, advanced the engineering to a very high level, okay? But if I make a commentary on Egyptian knowledge, it was a collection of many interesting and effective rules, okay? But the knowledge itself was disjoint. And the reason I say that, I'm going to explain later when I show you what one of the Greeks did with this knowledge, okay? Where I will show you the contrast between what the Greek did with this knowledge and what the Egyptians did with it. So what the Egyptians like to do was a collection of rules that the priests had, and they used it for all the practical circumstances, like building the monuments and so on. And in fact, they kept that knowledge within the community of temple priests. So they never had universities where they spread all their techniques and they tried to sit back and figure it out for themselves. Okay, they didn't have all that. Okay, that all came from the Greek culture, as we will see later. Okay, so this knowledge was not widely distributed, and the techniques were not spread out, so that in fact we still don't know how they built these wonderful pyramids. Okay, so once again, the Greeks absorbed all this knowledge from the Egyptians and the Babylonian cultures, and they were strongly influenced by their way of thinking and their way of projecting their civilization. So for example, if this is an Egyptian sculpture, you can see how the pose is, the stiff pose of the arms on the side. And this is a Greek statue. He uses the same techniques. Okay, it's got all the symmetry and everything, but he's influenced by that dignity and that poise, okay, of the Egyptian. So there was a strong influence of Egyptian culture in art into Greek culture. Okay, but again, I want to emphasize the Greeks were a maritime culture, and they took off in a different direction after absorbing all this knowledge. Okay, they took this new approach. And they began to ask new kinds of questions because of the fact that if they used this knowledge, they had to be sure that it was going to give them the right answer. And the reason is because they were a maritime culture, they had to know if the rules that they were using to tell how to go from one place to another and get back from where they came if these rules were correct. Otherwise, they would get lost at sea. Okay, so that would be a possible reason. So to give you a trivial example, they picked up the idea of the area of a circle from two cultures. Okay, so one culture said that the area of the circle is 3 times the radius of the circle squared. Of course, they didn't use this modern algebraic notation. Okay, and another culture said it's this prescription. Okay, take 2 times the radius squared and take 8 over 9. So now, which one is right? Okay, so these prescriptions motivated the Greeks to try to think about what is the correct way to figure out the area of a circle. Okay, and we'll come back to that. Okay, of course, you all know today that the area of a circle is pi r squared. And what kind of letter is pi? It's a Greek letter, right? And the reason it's a Greek letter is because it's a Greek who first figured it out, that it's that number 3.1417, whatever. Okay, we'll come back to that. But before I get to that example, I want to talk about Thales, who I call the first rationalist, one of these first thinkers. And he was one of the giants on whose shoulders Newton said he stood. Okay. Now, what he did was very important in 2 ways. Okay. He looked for, he absorbed a lot of these scattered factoids. Okay, like the prescriptions for figuring out the area of a circle. He absorbed these scattered factoids. Okay, and then he'd asked, okay, is there any fundamental order or rationale underlying these scattered facts? Okay, and then he went another step. So this would be important, let's say, for advances that Thales made in mathematics. But then he went another step, and this is really phenomenal when I get to it. He asked, after taking this example from mathematics, he asked, are there similar fundamental organizing principles underlying the vast variety of natural phenomena that we experience? Just like he was looking for some way to organize the different mathematics that he saw, he's trying to see, is there a way to organize what you see in nature? Okay, so this really is what we call the beginning of physics. Okay? So let me give you some examples, one example for each. So in his travels to Egypt and Babylon, Thales picked up these interesting prescriptions, and one of them was how to determine the height of a tall object like a tree. Okay, so of course you can take a ruler and climb the tree and so on, right? And it might fall off. But is there a clever way to determine the height of a pyramid or the height of a tree? And what he learned from the Egyptians is that there is a very nice way to determine the height of a tree. And that way is to stick a stick in the ground. And there's a Greek word now for this stick. It's called gnomon, G-N-O-M-O-N. If you walk down Eddy Street, there's a place called Gnomon Copy, or has it moved? No, it's moved downtown, sorry. It used to be on College Town. But gnomon is the basis of our word to know. All right, G-N-O-M-O-N. So this, you take the stick, all right, and you stick it in the ground. Now, you wait for a particular time of day when the shadow of the stick is the same as the length of the stick. Okay? When you find that time of the day, you quickly go and measure the length of the shadow of the tree. Well, then that is equal to the length of the tree, the height of the tree. Okay? And the reason is, okay, now he comes to the reason later. But the prescription is that. Wait till these two lengths are equal, then the length of the shadow is the length of the tree. So, prescription is that, but Thales figures out the reason later, okay, which I will come to. Now, the other point is that it's kind of inconvenient to have to wait till that particular time that the angle is 45 degrees, okay? It's inconvenient, okay? You'd rather do it at any point where there's a shadow. But then you need the more general rule. Okay, how do you use, for example, if you put a stick there, the shadow might be this long. How would you convert this shadow to this height of the tree? Okay, then you need to understand the fundamentals of what's going on with this simple prescription. And that's what Thales did. He figured this out. Okay, and that whole field of figuring this out, which you will review in section, is the mathematics of similar triangles. Okay, so from this particular application, very useful application, Thales advanced to the general principle of similar triangles. So I want you to pause here and think. Here he is progressing from the world of technique to the world of thought. Okay, not stopping with just the practical application and say, okay, I'm done, I figured out the height of the tree. No, he wants to go further. He wants to convert this Egyptian geometrical know-how into an abstract study, which is called similar triangles. So now he advances to the general principles, and once you advance to the general principle, then you can apply it to new circumstances, because you know the general rules, okay? And we'll do new circumstances here and in your section. So what are the new circumstances? So first of all, the most important new circumstances for the Greeks was to figure out how far is the ship, because they were a maritime culture, right? And how, if the ship is out on the shore and it's so small, how far is it, okay? So he first figured out the principle of similar triangles and applied it from that tree to the distance of a ship, okay? Now first let me just pause here for a second and explain to you what similar triangles are, okay? So here's one triangle with sides ABC, an angle ABC, whatever. And this triangle, if I draw a bigger triangle that looks just like the small triangle, but it is such that it's a scaled replica of the small triangle, then all the angles here will be the same. This angle is equal to this angle, the top angles are equal, and the side angles here are equal. These are two similar triangles, but the sides are not equal, right? Because one is scaled version of another. But when you make two similar triangles, then you come up with a relationship between the sides of the two triangles. Okay, and that's what you learn in geometry. The relationship is that the ratio of the small side A to the big side A here, sorry, you cannot see the line, there's a line here. A over A equals B over B equals C over C. Okay? That is the heart of similar triangle geometry. That's what you use to apply it to the general circumstance, okay? And Thales is the guy who figured this out. And now he applied it to this situation of how far is the ship from the land, okay? So we will repeat this in sections, so I'll go through it a little bit fast. But basically what you want to do is you have an unknown quantity called the distance, right? From the eye to the head of the mast of the ship, right? Okay? And you know something. You have to know something. You have to know the height of the ship, okay? Now, he knew the height of the ship because the ships were all made in the shipyard in Greece. And so he just went there to the ship maker and said, typically, what is the height of your ship, okay? And he would learn that the typical height of the ship is h, because most Greek ships had similar mast height. So he had that knowledge. Now, he needed to measure the properties of a small replica triangle that he put over here next to his eye. So here's your small triangle, which you stick next to the eye, and you overlay, just like you're trying to make those that triangle on the ground, overlay the big triangle of the tree. You overlay this little triangle onto this big triangle till the two are similar, have all the same angles, okay? And if this triangle, this small triangle, is similar to the big triangle, then I can write down the mathematical relationship. If these two sides are x and y, I can say x divided by y equals d divided by h. Okay? And now the problem is I don't know x and y. But x and y are small triangles that I can draw on the sand and I can measure. You follow? So if I can measure this on the sand and I know what h is, the only unknown in this equation, I know x, y because of my sand, and I know h because I know the height of the ship. The only unknown is d. I can solve for d, because he didn't do all this algebra, he just did it in his head, okay? Simple multiplication. You can solve for d by this simple algebraic operation. Now in the modern approach, we don't draw triangles in the sand, okay? We have what we call trigonometry tables. Okay, it's the same thing, right? We make all kinds of angles, and we tell from that table what is the ratio of x over y for many, many different angles. Okay? So we just go look up the trigonometry tables that tell us what is x over y. So that's what this means. The modern approach is you match up the angle theta to the angle which the ship subtends to the eye. This might be a new word for some of you. Subtend to the eye. Okay? It means you look at that object and you take the rays of light that come from the top and from the bottom and you collect them in your eye. The angle that these two rays of light make is called the subtended angle. Okay? So, or you can look up these tables and figure out what the so now you can apply the similar triangle principle to all kinds of situations and use it to determine the distance. All right. So now we're ready for your next question. Okay, now this is the hard question. Okay, remember I gave you one easy question, one hard question to help you with the quiz. So this is a help for your quiz question, okay? It's a modern question for you. Determine the distance from the Earth to the Moon. All right? So the issue here is, I want you to think of the Moon as a ship in space, okay? And draw on your pages a similar diagram to what I just drew, okay? Is it there? There. A similar diagram to that. And figure out what quantities you're going to need to calculate the distance from the Earth to the Moon, and what quantity you're not going to need, all right? And pick out the quantity that you're not going to need, and mark it. Here's the diagram that you were supposed to have drawn. So there's the Earth, there's the Moon, and there you are. And so you draw a line from the center, from where you are to the base of to the center of the Moon, and you draw a line to the top of the Moon. So you need to know the size of the Moon, just like the Thales needed to know the size of the ship. Okay? But you measure this angle, and you look up, if it's a quarter of a degree, you look up the tangent of a quarter of a degree. And what it says is that when the angle is quarter of a degree, the base is 230 times the height. So if you know the height, you know the base. It's 230 times the size of the Moon, the radius of the Moon. So that's the diagram that you should have on your paper. And so this radius is irrelevant. Okay? Now, I might ask you to find the distance from the Earth to something else. There's another clue for you. Okay. So, coming back now to Thales and his derivation of general principles, okay? I want to point out that his interest in geometry was particularly germane to the fact that geometry was a very important aspect of other parts of Greek culture, namely Greek art and Greek architecture. So you can see, for example, in the vases of this, what we call the Greek geometric period, that they are interested in triangles and circles and so on. And here's a nice picture of a vase decorated with many, many circles. And when I first wrote the draft for this book, I wrote that the Greeks probably used a compass to draw these nearly accurate circles. Okay? And I gave this to a Greek scholar at Columbia University to review this chapter in particular. And she X'd out probably. So I said, why did you do that? You know, how do you know for sure? She says, we know for sure because if you look at any of these circles up with a magnifying glass, you find a little hole. So they actually had a sharp instrument that they used to, dig a hole and then draw the circle around this thing. So they had a compass. Okay, this is the Greek period, okay, before 600 BC. All right. So here's a nice example of Thales absorbing geometry from Greek culture and extending his ideas to generalize. Now I'm going to go to physics, because that's really what we're interested in. Is Thales' most important contribution was to ask questions about nature, about the physis of the world. Okay? He coined the word physis as the nature of the world. That's where physics come from, okay? Right from Thales. All right, so that's the origin of our Greek word. And he asked particular questions about different aspects of physics, okay? Like, what is the nature of matter? Or the stuff that we, feel in our fingers when we touch the earth and touch the tree and so on. Why is there so much variety in matter? What is the shape of the heavens? So questions like this dominated his thinking. Now the interesting point is that he tried to come up with answers to these questions. And he had very little to go on, agree, compared to what we have today in terms of tools and a knowledge of each other's thinking. So you must take his answers with a grain of salt, all right? So the answers itself don't get too serious about, okay? But just try to think about his way of thought, okay? How to approach the question. That part still survives, okay, his method. But his answers are not correct, but that's all right. So this was a new style of philosophizing, and we might call it guesswork, speculation. I'd prefer to call it a real insight, okay, into what's going on. And I want to emphasize to you that this insightful kind of guesswork is always going on in the progress of science, even today, okay? Because science is a creative activity, But we don't just go free for all, okay? Anything you feel like, okay? We are guided by certain aesthetic principles, as I mentioned in my introductory lecture. So we choose certain options guided by aesthetics. So what is the aesthetics that guided Thales? The aesthetics that guided Thales was the idea that underlying all this diversity that you see in nature, there is some unity. There is something the same all the time, okay? What is that? So in coming up with these creative answers, Thales was led by this aesthetic principle that there must be this underlying unity behind this diversity. And therefore, he says, tree, rocks, air, all the stuff that we see, is all made of the same thing, okay? There's only one single fundamental substance of which everything in the universe, well, everything on Earth, let's say, is made, okay? And he called that the element, the primary element. So again, we have survived, that word element is survived in our culture, okay? We look for the elements. Of course, we know that there's not one element, but many. But he says everything's one element. And that's a really bold idea, because we're still fascinated by, trying to find out is there one element from which everything else originates, okay? We're still captivated. We don't have the answer to that yet. But the point is that Thales was, again, thinking about such a deep question. So that was Thales' primary element. What is that? But my picture is not so good, huh? Water, right. Okay. So Thales chose water as the primary element. Why? Well, he lived on an island, come on. So, water was everywhere, abundant, okay, and sort of the basis of everything. And so he chose water to be and the other very important reason why Thales chose water was because he recognized that just like all matter has different forms, some matter is liquid, some matter is solid, some matter is gas. Okay, you knew all about gas, okay? So that when you think about water, it takes on all these same forms. Okay, water can be a solid like ice, or it can be a gas like a vapor that turns into beads, and it also changes from one form to another, which then would explain why this is the fundamental substance, because it can transform to all the other substances. Okay, so water assumes all these forms. So he saw every morning the moisture in the air condensing like dew, on the leaves. Okay, so he could see the transformation from water vapor to moisture, and he could see when it got really cold. For example, if he went on top of Mount Olympus or something on one of his hikes, he could see these snow crystals. Of course, he didn't see all this beautiful picture that I show you about snow crystals. Okay, he just saw this white fluffy stuff. But the point was that it was solid. Okay, so a vapor, liquid, solid. Water must be the heart of everything. Now that's one example of Thales thinking about physics. Okay, here's another example, which is what I call cosmology. Okay, again, Thales is trying to get a picture of what the universe looks like. Okay, so he says, the Earth must be a giant rock floating on water. Okay, so the Earth is a rock floating on water. So there's this universal sea of water, just like a Greek island. Okay, and these heavenly elements here, they are on a hemispherical canopy. Okay, they're stuck on a hemispherical canopy. So I want you to think for your third question, why do you think he floated the Earth on water, and why did he fix the heavenly bodies to a canopy? That the cosmology that he worked out had a reason, So for example, he chose the Earth to be a flat disk because when you look out, the Earth looks flat. So he had to start with a flat disk, okay? And he was worried like everybody else as to what keeps the Earth falling down, just like everything falls down. Why doesn't the Earth fall away? So he has supported, he floated it on water. And the stars attached to the canopy, that's trivial, right? He just stuck them on the fabric of the canopy so that they don't fall down, okay, like candles, okay? And the reason he chose a hemispherical canopy, again, is because when you look up there, the sky looks like a bowl on top of you. Yeah? So this is a very important question, because I want to emphasize to you how Thales was basing his cosmology very strongly on observations, okay? Just very founded in observations. This is going to be very important, because I'm going to come next to the philosopher who basically kicked all his observations into the dust and started basing his cosmology on ideas, okay? So we'll see how the whole struggle between trying to think in terms of observations or think in terms of ideas, is constantly battling one another. All right, but don't be upset, okay, if you didn't get it, right? So Thales chose water, right? And as I said, one of the wonderful components of Greek culture was debate. Okay, so the philosophers who came after Thales said, you know, Thales, you missed a lot of stuff. Okay, what about, yes, water is good, but what about earth? You know, and there's fire. I mean, I don't see how water can make fire. Okay, so they debated with Thales, and they came up with these alternatives, and that was this competitive spirit of the Greek culture. So you have, you know, this guy making fun of his master, and the other guy saying, don't forget about fire. And then there's another element that they create called ether in order to explain the fiery nature of the stars. Okay, so they came up, the Greeks then, philosophers after Thales, came up with the 5 elements, water, earth, fire, air, and ether. What's amazing is that these 5 elements are present in many, many cultures around the world. Okay, so if you go to Hindu culture, they have the same 5 elements. Okay, how they got it from the Greeks, I don't know, but or maybe it's the other way around. I don't know. Okay. All right, now I'm going to talk about this other scientist that came after Thales that kind of contradicted a lot of the stuff that I talked about. And his name was Pythagoras. And I'm sure you heard of Pythagoras, right? Why have you heard of Pythagoras? Pythagoras' theorem, right? That's a favorite theorem, right? So what was his theorem? By the way, he was a contemporary of Confucius in China and Buddha in India. So again, my point that sort of the world is waking up at around the same time, okay? So the theorem is that if you have a right triangle, and this is again something he learned from the Egyptians, then you can define a relationship between its sides. Okay? And the way that he defined the relationship between the sides was extremely different than what the Egyptians did. He said, draw a square on each side. Okay? So you draw a square on the small side, draw a square on the big side, and draw a square on the hypotenuse. Then the area of this square plus the area of this square equals the area of that square. Okay? That is Pythagoras' theorem. Okay? Normally known to you as a squared plus b squared equals c squared. But what it literally means is that these are the areas. Okay? And the proof he gave, I'll show you, you will see an example of the proof and many others. But he didn't really give a strict logical proof, which was up to Euclid many hundreds of years later. Okay, but nevertheless, he had some proofs based on symmetry. Now, again, mathematics. Now let's go to physics. What did Pythagoras do for physics? He seeded 2 important ideas for physics, okay? One is, again, as I said, creative, right? Creative but guided by aesthetics. So, the first idea, he says, is nature is beautiful. Because, you know, we know that nature is beautiful, but he meant something deeper, okay, and I'll come to that. The second idea, which is what you've learned a little bit in section, is that there are patterns, there are mathematical patterns in nature, okay, or that the regularities of nature are intrinsically mathematical. So when you look at any kind of natural behavior, you might find that it obeys some interesting mathematical pattern. So these are 2 important physics ideas of Pythagoras, and we'll go through these in the next session. Okay, so let's get back to the first idea. What did he mean by nature is beautiful? So what he's saying is that there are aspects of nature that look chaotic, but if you look hard enough, you will find these things. You will find symmetry, you'll find elegance, you'll find order. So for example, the wonderful peacock, you know, you stare at it, you're just mesmerized, okay, by its wonderful pattern here. But there really is, behind that beauty, there's a symmetry. Okay, and actually there's more. There's a mathematical pattern in this, which we might talk about. Okay. So the important thing is you have to be able to find it. You have to look for it. Okay. So it's not just the beauty that appeals to you. And so he is the guy who, by the way, coined the word cosmos. Okay, from which is based our word cosmetic, right? To make yourself beautiful. Okay. All right. So if you look at nature, okay, you see all these wonderful things like the rainbow, which you will inevitably, if you see a rainbow, you'll stand there and you'll stare at it for a while, right? But you don't quite know why you're staring at it. But it is beautiful, and there is a tremendous amount of mathematics in that, tremendous amount of symmetry in that, and we will discuss that. The guy who really explained the rainbow was Isaac Newton. Okay, so that means we have to wait a while. Or if you look at a tree, okay, you see a beautiful symmetry pattern in the way nature organized the tree, the leaves of the tree. We'll talk about that. for sure. Or the beautiful flowers, okay? What's the beauty in the flowers of nature? So we'll talk about that. Or the snow crystals on top of Mount Olympus, okay? There's a wonderful property about snow crystals. This is really, when I heard this the first time, I thought, it's really amazing. No two snow crystals are the same, okay? Every single snow crystal has a different pattern than another, okay? It's really amazing. And it grows in a completely symmetric pattern. And we'll see the reason for that, okay? Or the Nautilus shell, which I'm sure that they were very familiar with, it has this mesmerizing spiral, okay? That also has underlying beauty and symmetry and mathematics to it, okay? Which we will discuss. So the simple definition of symmetry, which you've talked about in section, is symmetry is a repetition of a particular quantity. Like if I cut here, this part repeats itself on this part. So that's a simple definition, bilateral symmetry. Or translation symmetry, okay? So examples from art and mathematics. There's an example from art with bilateral symmetry. There's an example from architecture of translational symmetry. Do you know what this structure is? Parthenon, right? The Greek Parthenon. But it's in its original form, right? It doesn't look like this anymore. It looks like that, right? Because they had so many. Does anybody know what was the biggest occasion that destroyed the Parthenon? Yeah, I think the Turkish people stored the ammunition there, when they occupied it, and then the British blew it up. So that's what happened to the Parthenon. But anyway, it still stands there, and it's still quite majestic, and it was right here in the middle. There was the statue of Athena that I was talking about. So you can see that you have reflection symmetry here, you have translation symmetry, you have all kinds of symmetry. So just pause for a second here and think about our culture some more now in terms of the Greek developments. You can see a lot of roots of our culture in the Greek culture. Okay, so for example, our wonderful stadium there. Okay, that's your Greek stadium. That's our stadium there. Okay, that comes from the Greek culture. Okay, that stuff. What's that? The White House, right? That's part of the. That's part of the Parthenon right there. Okay, and what's this structure called? Very important for us. The Supreme Court. Yeah, the front of the Supreme Court. Then if you walk around campus, you'll see this, right? Again, Greek culture. And in fact, all around your culture, you guys have Greek societies, right? Alpha, beta, gamma, beta, tau, etc. You guys are all inspired by, who? Pythagoras. He was the first guy who formed the first fraternity, right? Of brotherhood. People who followed him because he was so inspiring, and all the stuff he said was just follow. They abandoned all their possessions, they abandoned their families, and all. They just followed Pythagoras because you're not going to do that, right? You're going to continue your studies. Okay. Now there's another definition of symmetry, and that is there exists a symmetry whenever there is a quantity that remains unchanged under an alteration. Okay, that's a little bit of a more advanced definition. So there's a nice example here. So you have this basic soldier. But if you translate the soldier, you get the same soldier, and you translate, you get the same, approximately the same soldier. So there's a change under the alternation of translation, and so this is called translation symmetry in art, okay? We call the dancing soldiers. Here's another example of the translation symmetry. But you note that these symmetries, as the artists have depicted them, they're not perfect, okay? Because, there are some perfect. If you look up there, okay, they got a perfect pattern, okay, perfect design that repeats itself. But here, they didn't make it perfect because they're representing humans, okay? And, the artists, they recognize, that humans are not all the same. And unlike these rigid designs, the human shapes and rhythms must not repeat, okay? So to the artist, this delicate shift represents life and nature, okay? Flowing forms, okay? But there is an underlying symmetry that governs it. You don't want to stick to it exactly because then it's boring, okay? So being true to nature, the artist was sensitive enough to avoid it. Okay? So nature hardly exhibits perfect symmetry, but if you're a guy like Pythagoras, right, then what you have to do is you have to look at nature, you have to examine it, okay, and even though you don't find that obvious symmetry there, you look beyond it, okay, with the mind's eye, okay, you look beyond it with the mind's eye, and you find the symmetry in it, even though you can't see it, all right? So I'm now taking you further into Pythagoras' mind, okay? So now we come back to how he throws Thales out the window, okay? So he said, okay, here, Thales, my man, let's look at your cosmology, okay? You've got this universe, this hemispherical sky, and all these stars attached to the hemispherical canopy. And he says, it can't be, it can't be that the sky is a hemisphere. I mean, the sky should be the same all around you, okay? So there was a deeper insight, okay? He sees this asymmetric object, okay? But he has a deeper insight based on symmetry. So even though Thales said that when we look at the heavens, we see a hemispherical canopy studded with stars, Pythagoras says, no, the universe, the heavens must be spherical around us, okay? So he dismisses this canopy, okay? And he replaces it with a spherical universe, right? So why? Because it's beauty, it's symmetric, okay? You missed that symmetry, okay? Just like that, if you look at that vase, you missed the symmetry, but if you look carefully, the soldiers actually have translational symmetry. So you missed it, really. Okay, let's look at the sun and look at the moon, all right? So if you look at the sun and the moon, you say, Thales says, the sun and the moon look like this, right? They do look like this. In fact, Homer said, and so, and Achilles carried the warrior's shield like the sun, and the moon, and so on. Somebody else had a shield like the moon. So all the shields are this shape. And Pythagoras says, no. The shield is baloney. Throw the shields out. The sun and the moon look like this, all right? And they're far away from you, okay, some of the people in the back, you still see the same, right? You see this. You see a round circle. But nearby you can see the side, okay? But from far it looks like this. And we're far from the moon. And we're far from the sun. So it looks like this. But why do I prefer, I'm Pythagoras, why do I prefer to say that the sun and the moon look like this and not like this? They look like this. Why are you saying they look like that? He says, because if I rotate this, it looks like what? A line. So here's your sun now. All of a sudden, somewhere else, it looks like a line. Can the sun be a line? No, you want that sun to be always a disk. Doesn't matter where you're looking at it from. Your sun should always appear like a disk. Okay. So again, he goes beyond what he sees, uses the eye of his mind to say that the sun and the moon must be spheres. And now he goes to that next step, which is really the amazing step, which is that the Earth itself also must be a sphere. Okay. So this flat disk that Thales had, floating on the ocean, baloney, must be a sphere. The Earth must be a sphere. So Pythagoras was the first person to theorize, okay, that the Earth must be a sphere. Okay. So just quickly review this. The sun and the moon look like disks, but we have the choice, okay, and I did that demo. So the sun and the moon are not spheres, are not disks, they're spheres. And he chooses that based on the symmetry, okay, of the sphere. And I showed you the symmetry, okay. And now this is this big jump, okay. Even the Earth must be a sphere. Now, as we progress here to the next lecture, you'll see that there were other philosophers who came after Pythagoras who said, you can't just go ahead and say that the Earth is a sphere, you must have some proof for it. And so they did actually go ahead and find some proof that the Earth is a sphere. So we'll talk about that. But the thing is that Pythagoras figured it out without any of that proof. Why? How? Creative thinking guided by beauty, aesthetics. Right? That's always the case. Right? Scientists are always guided by these fundamental aesthetic principles. So that's what Pythagoras had done. Okay, so now comes your last question. Why did his contemporary said, Pythagoras, you're a fool. Get out of here. Why did they say that? That's the correct answer, all the above. Right? But what I wanted to really show you, was trying to hide, was this picture here. Okay. That's the reason why they said you're wrong, right? which is what you saw. Okay, see you next time.